So in office hours today, there's a couple questions that we're going to be doing just based off of the people who are in office hours today asking questions. We're going to look at absorption prep activity 1, problems 2 and problem 7, absorption prep activity 2, problems 4 and problem 5, and then mastery question set 1, problem 4 and problem 5. We can kind of do abs 1 both at the same time. So what we're looking at in this problem is we're really looking to get an understanding of the difference between apparent color and interaction color. You can all hear me still, yeah? Cool, great. So when we look at something that's green, most of us learned in high school or elementary school at some point that it's green because green light's bouncing off of it. Right? And that's a very observer-centric way to think about it. We're thinking about this apparent color simply in terms of what wavelengths of light are making it to our eye and how that observation appears to us. In a chemistry class, we're actually more interested in how the wavelengths of light are interacting with the material. And so we get this difference between the apparent color and the interaction color, or the color that's being absorbed. If you looked at the simulator, for any one of those things, you can imagine you have this little slider and you can change the wavelengths. And in my mind, whenever I'm doing that, I'm actually making a plot in my mind of absorbance versus wavelength. And if you look at that for the red materials, we're going to have a wavelength range from something like 400 nanometers in purple light all the way up to something like 700 nanometers for red light. And it turns out, I'm going to try to break this up a little bit. Red, orange, orange, yellow, green, blue, call it violet. Okay. So when we look at something that appears red, and if we put it into a spectrometer, if you watch the absorption lab activity video posted to Canvas, you'll see that there's a device called the spectrometer where we could take the dye out of this pen, we could put it into the spectrometer, and we can look at the wavelengths of light it absorbs. And we're probably going to notice that it's going to absorb in the green area. So the apparent color, the color of the solution to our eyes, is red, but the wavelength of light that's actually interacting with the chemical compound is green. What that first prep activity is asking us to do is essentially create a list. Because LabPal is designed mostly to interact with numbers, it asks us to kind of make a list of whether light's being absorbed or not. And so that list would correspond to the Roy G. Biv. And for this one, we've got nothing absorbing in red. So that would correspond to a 0. Orange doesn't really have anything corresponding, absorbed, so that would correspond to a 0. Yellow doesn't really have much absorbed. Green does, so that would get a 1. Blue doesn't, and purple doesn't. So this would be our absorption list, and this is what it's asking us to enter as a column of numbers, an array. And that formatting has messed up a lot of people in that prep activity. But you do need to use the PhET simulator in order to look at that. And we can see that if green is being absorbed, everything else is being transmitted. So it's not just that red's not interacting with this material and bouncing off of it, but red, orange, most of the yellow, the blue, and the purple are all bouncing off of this. And our brain collects that information and says, yeah, that's red. We'll call that red. Now, I don't have a purple pen, so I'm going to do it in orange. Let me first check. Does that make sense? So that was Lamb who was asking that. Lamb, does that make sense for what you're doing in part 1? I'm going to assume yes and go on to problem 7 of ABS 1. So in this one, it's asking us to look at a different compound. The activity has us go through several different compounds and look at the color it looks like on the screen versus the wavelength of absorption that actually occur in that. So if you get your laser, you get your variable thing, you start sweeping it through the different colors. And what you notice for that purple solution is a peak. And I just helped somebody with this earlier today, which is why I know where the peak actually is. For potassium permanganate, chemical formula KMnO4, we get one peak. And that one peak is somewhere between green yellowish. So we can look at this and we can say, okay, there's only one peak. It's mostly on the yellow side. And in that way, it makes sense that this peak would give rise to an apparent purple color, because purple, blue, green, orange, and red are all making it to our eye in giving that appearance of purple. Some people think of it just in terms of the blue and the red. If you think about this in terms of mixing two colors like we do in elementary school, you mix blue and red and you get purple. Here, when we're thinking about it in terms of light and what wavelengths of light are actually interacting, I actually have something purple. So when you're looking at something that actually has a purple color to it, you can kind of think, well, what gives rise to that particular purple? It could be that this is a combination of blue dye and red dye, or it could be that there's just one dye in here that happens to absorb in the yellowish range, and that gives rise to purple. So there's different ways that we can actually get colors, and the thing that's really neat to me about this is this gets us to the point where we're starting to think about not just what we see, but how the chemical compounds give rise to what we see, right? It's really thinking about how does the light interact with the material. That's the essence of what we're looking at here. So you've got to play with this. But there's another possibility, right? If we looked at the blue thing, blue has a peak over here in the orange range. They don't actually get higher like that. I'll call it blue looking. Something that looks blue. Doesn't interact with blue light, so yeah, blue light's making it through, but so is purple and green and yellow and red. And it's really the molecules that make up this blue dye are interacting with just the orange light. So if we mixed the blue and the purple, or sorry, the blue and the red, we'd get something purple. Or if we just had something that was doing yellow, we'd get purple. And it's that difference between our observed color versus the actual way that the chemical compounds are interacting with the wavelengths of light. Does that help you out, John? Does that make sense?
Yeah, it does. So because for that question, I actually said that, I wasn't too sure on how it was, what was being absorbed or how it was being transmitted. So you're saying that the lights that are able to be transmitted through is what we can see?
Yes. Yeah.
Okay. I said, yeah, for that particular question, I was like, oh, well, I looked at, red and blue, and there's a high transmittance of those two colors. And I was like, well, since red and blue is going through, then like those two colors make purple, and that's why it appears purple to us.
And that's a perfectly fine way to think about it. It turns out, again, that's mostly about how we observe it. In a chemistry class, it's more interesting, at least to me, to look at how the chemical compound that gives rise to the color is actually interacting with the light. Right, just kind of shifting that focus from what I'm seeing to what's actually happening to the chemical compound.
Right, thank you.
Cool. So for those of you that just came in, the questions I have on cue, you can go ahead and throw your questions in the chat and I'll get to them. Right now we're about to move on to absorption 2, question 4 and 5, and then mastery question set 1, problems 4 and 5. And if you've got other questions besides those, you can throw them in the chat window and I'll get to them. So absorption 2, part 4. Yes. Let me check something real quick here. I want to check how this thing is doing its calculation in the background so I don't mess up my answer. But so what prep activity 2 is looking at, it's asking us to create some relationship between a yellow dye with information given, and then trying to figure out how we can get at not just what we see in terms of the yellow dye, but some information in terms of what's happening with that chemical compound. And the neat things we can do with that is we can start to get, okay. Okay, cool. Just making sure. There was a difference in the ways that people set these up. So making sure I'm looking at the right problem still. Prep 2. Problem 4. Use your standard curve to determine the concentration of an aqueous solution of the yellow dye that gives an absorbance of 0.42 measured at a wavelength of blah. If you went and watched the Beer's Law video, you know that the wavelength information is kind of essential because you'll notice as we sweep wavelengths, the dye absorbs in different places. This is a yellow dye, so I'm going to go ahead and put a yellow curve. If we had a yellow dye, what color, well, it's hard to ask questions in this version of office hours, but if we had a yellow dye, think about the answer before I put it, it's going to absorb it should absorb in the purple area, the complementary color, right? This is looking at how the dye is how the light is interacting with the dye. And all that matters, you'll notice as the wavelength changes, how much light is absorbed changes. So we're just going to measure right here at this peak. And so we're going to measure the highest point, and that's going to be about 429 nanometers. But after we have that, and we know we're observing at that peak, that wavelength is not going to play a role in our calculation anymore. What we're going to do is instead of looking at just one solution, we're going to look at a series of solutions with changing concentration. And if you look at the data, you notice the peak gets lower and lower as the concentration goes down. And instead of doing a plot like this, we're going to change to a plot of absorbance versus concentration. If I'm going too fast, or if you've got questions about what I'm saying, feel free to chime in. So we're switching. To do absorbance versus concentration, only at that one wavelength, right? So we picked our wavelength, and we're going to see as the concentration goes up, the absorbance goes up. And we get this linear relationship. I have an easier time drawing straight lines when they're dashed. That's why I keep doing dashed lines. So we get this linear relationship between absorbance and concentration. Now what this allows us to do is I could take any, even though I only had like a few data points, I could now say, well, if I had some absorbance that was here, I could relate that to some concentration. By plotting the data in some y versus x way, I have some relationship. And so now any absorbance I measure for this yellow dye at this wavelength, I can figure out the concentration. We're going to do it with the actual data. And so when you make this plot, you should get a linear fit, and you're going to get some equation that's y equals mx plus b. And when you do your plot, you've got some value for m, the slope. You've got some value for b, the intercept. And those two things you just get directly from doing the Excel plot. If you're still a little shaky on how to do Excel plots, there's a couple videos on how to do this on the Canvas page in the week 1 information. And if you want me to, I can open up Excel and show you how to do a couple of those. But at this point, after we have this equation, we're going to be plugging in whatever this is for a given absorption. So in question 4, we have a given absorbance of 0.42, and we're asked to find the concentration. So we know what y is. We get slope and intercept from our previous work, and then we just solve for x. It'll take me a little bit to set that up and actually get the answer, so let's see. And then problem 5 is actually the same idea. So, do me a favor, answer yes or no to this question. If you click on participants, you can answer yes or no. Yes, no, you want me to do an Excel plot with a shared screen right now. Mostly no, couple yeses. Those of you that are, oh, yes is winning now. Okay, I'll go ahead and do that real quick. I'm gonna pause my screen recording. One of the things that's most important about this equation, and the reason that this works, is this connection between our mathematical understanding and our chemical understanding. So what we're doing when we do this is we're mapping our mathematical understanding, y equals mx plus b, our y-axis and our x-axis, and we're mapping that to our chemical understanding in terms of Beer's law, A equals epsilon bc plus approximately 0. So if we have a perfect solution, how much light is something going to absorb if it has nothing in it? Theoretically, should be nothing, right? Theoretically, you have a 0 intercept. So we can see that the intercept is theoretically 0. For us, since we actually do have an intercept, that's because we're using experimental information. We're using things that actually have some deviation from the perfect idea. Our x-axis is the concentration. Our y-axis is the absorbance. And what that means is the slope of this line is actually going to give us some chemical information about our compound. Right? This is absorbance. This is concentration. That slope is going to be epsilon times b, where b is the path length. That gives us some experimental information. But epsilon is really a property of the chemical compound we're looking at. So this epsilon is actually getting us information about how that chemical compound behaves. So that was problems 4 and 5 in absorption 2. Next up on the queue is mastery questions, problem 4 and problem 5. And if you've come in recently, you can go ahead and put your questions in the chat, and I'll just keep going through them as they come up. 4 and 5. Ah, yes, these are fantastic problems. Really just exceptional. So, mastery question 4 requires us to read the background. Mastery question 4, this is set 1, problem 4. It is really kind of a bridging problem. It almost fits better in next week, but there's nothing wrong with getting a little ahead. So we're looking at mastery question set 1, problem 4. And it's asking us to look at some of these properties of light. In my opinion, it's got a little bit of an obtuse aspect to it, where it gives us this energy based on raising a mass. So I'll read the problem, and then we'll break the problem down together. Let me check something real quick. There were a couple people asked about this. So how many moles of photons with 665 nanometers, my numbers might be different than yours, wavelength are equivalent in energy to the energy change associated with raising a 58.6 kilogram mass by 1.74 meters. Use the formula blah E equals mgh and use g equals 9.8 meters per second squared. So this is happening on Earth. That is the gravitational force of Earth, 9.8. Okay, that's a whole lot of stuff. Let's start breaking down the problem step by step. First thing I always do when I'm looking at a problem is I just start writing down the information they gave us. We've got wavelength equals 665 nanometers. We've got a block. We've got mass equals 58.6 kilograms. We've got a height of 1.74 meters. We've got a gravitational constant of 9.8 meters per second squared. And we've got an equation. Energy equals mgh. And then also really important to recognize in the problem before we start hitting our calculator or any of our problem solving is what is the question actually asking for? It's asking for how many photons, right? So we've got to relate this energy of the block to some energy related to the photon in order to get to how many photons to have these two energies equal to each other. This is all of our explicit information, the things that are given inside the problem for us to work with. And there's some implicit information. There's something missing here that we need to get in order to do this problem. And this is where we have to read the absorption background information pretty carefully. There's an equation for how we get the energy of a photon. Ooh. Oh. So the energy of a photon, hc over lambda. That's in the background of the absorption lab. It's also on our equations sheet. If you haven't been using the equation sheet from the modules portion of the Canvas page, the equation sheet is really handy. That's the energy of a photon. But there was nothing in the problem that told us to use that. So that's the implied information that the problem was assuming we could figure out to do it. At that point, we can start kind of doing some algebra. I'm going to start with just the photon energy, and then we'll come back and deal with the block energy. So again, using that equation sheet, we've got a couple numbers. H is a constant, C is a constant. H is called Planck's constant, 6.626 times 10 to the minus 34 joules seconds. Didn't give myself enough space. Speed of light is 2.99 times 10 to the 8 meters per second. Wavelength is 665 nanometers. And I'm going to go ahead and do 1 times 10 to the minus 9 meters per 1 nanometer to convert it into meters. It's really important that we're consistent with our units. So you notice because the speed of light is in meters, the seconds is going to cancel out. Nanometers will cancel out there, meters will cancel out there, and I'll just be left with units of joules. I'll get something that's an energy, which is what we wanted to get. Go ahead, grab your calculator, and you should all grab your calculators and calculate along with. So we'll go ahead and do this calculation real quick. 6.626, oh, typo, 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 is equal to that, divided by 665 times 10 to the minus 9. Oh, I had a typo someplace. 6.62, oh, I did negative 8. How silly. Minus 34, 2.98 divided by 665 times 10 to the minus 9. There we go. My photon energy, and one thing that I'll point out, a good rule of thumb, if we're ever dealing with light that's in the visible spectrum, we expect an energy that's on the order of negative 19 joules per photon. We get 2.979 times 10 to the minus 19 joules per photon. But that's not what the question asks for, right? It asks us for kilojoules of energy per mole. So we'll do a couple conversions to get this in the units that the problem wants. I like these units, but the problem specifically says it wants kilojoules per mole of photons. So the first thing I'll do is I will say 1 kilojoule has 1,000 joules. And then I'll do 6.02 times 10 to the 23rd things per a mole. So this is Avogadro's number. It tells us how many things are in a mole. That number of things could be photons, could be electrons, could be ions, could be molecules, could be anything. That's why I leave it as things. In this particular problem, it's going to be number of photons. We go ahead and we plug that into our calculator. 2.979 times 10 to the minus 19 divided by 1,000 times 6.02 times 10 to the 23rd. And I get I get 179.3 kilojoules per mole of photons. I'm going to erase that. So again, because mole is just a things, I like to put specifically what the thing is that it's keeping track of. So that's moles of photons. That part of the problem, I'm going to move that up here. And that's the first part of the problem. 179.3 kilojoules per mole photon. Now, I want to figure out how many moles, so I get a kilojoule, I get 179 kilojoules of energy for every mole. How many moles of energy would it take to move this mass by this amount? Okay, a little bit of a side nerd thing for a moment. I know you're all nerds because you're at Cal Poly and you're taking chemistry. I'm also a nerd. I hadn't thought about this before, but this is, you can think of this as light pressure. You could actually use laser light to lift objects. If you had enough energy in the laser light, you can push things around. It's kind of neat. That's part of how some objects in space travel, is they actually use solar radiation to push them, solar sails. It's neat stuff. But then you don't have to overcome gravity. So let's go ahead and figure out how much energy, nerd moment over, let's figure out how much energy we have here. So our energy in this case is going to be, from the equation that was given in the problem, 58.6 kilograms, kilograms, times 1.74 meters, times 9.8 meters per second squared. Plug that all into my calculator. .6 times 1.74 times 9.8, and I get kilograms meters squared per second squared. So we get 999 kilograms meters squared per second squared, which seems like weird units, but these weird units actually combine to give us one unit, kind of like the way that moles per liter gives us molarity. Kilograms meters squared per second squared combine to give us joules. So this is actually in terms of an energy. It's in joules instead of kilojoules, but we can fix that real quick. 1 kilojoule has 1,000 joules, and the energy of gravity is going to be equal to, I can do that one in my head, 0.9992. Ta-da! So we're not done, because remember, how many photons, right? That's what the question is actually asking for. So when we look at this, we say, okay, well, based off of these two things, this is kilojoules. I have 179.3 kilojoules per mole, and I've got less than a 1 kilojoule, so I should need something a lot less than a mole of photons. And you can see just by dividing these two, doing a little bit of unit analysis, if you do 0.999 kilojoules times 1 mole of photons has 179.3 kilojoules. The kilojoules will cancel out, and I'll get something that's just in terms of moles of photons. And that'll get us the answer. So I'll take that 0.999, divide by 1,000, divide by 179.3, and you should get something, if you had my numbers, you should get something that's like 0.00557 for the final answer. Now, I don't actually, even though that's the most straightforward way to get the answer for the problem, I don't find it the simplest conceptual way to think about it. What I like to do, so first off, this is a fine answer, it gets you the right answer. But the way I like to think about it is a little bit different. And I'm going to go over that real quick. So I like to think about it back to that number we calculated before, where we had the energy of the photon in terms of just the single photon. .185 times 10 to the minus 19 joules per photon versus 999.2 joules. And the way I like to think about this problem is actually, well, how many photons is it going to take to get to that number of joules? And the reason I like this is because it gives you a better idea of the scale and the kind of number you expect, right? The energy for each photon is a really small number, right? 10 to the minus 19. So if I wanted to just get 1 joule of energy, I would need 10 to the 19 photons. I would need a huge number of photons. If I want to get all the way up to 999 joules, I would again do my unit analysis, and I would do 999.2 joules, and I would multiply 1 photon has 2.18 times 10 to the minus 19 joules, and I'm going to get a huge number of photons necessary to get to that. 999.2 divided by 2.185, that's 10 to the minus 19. 4.573 times 10 to the 21 photons. Right, just a huge number of photons. And then we can figure out how many moles that number of photons is, where moles is just another way of a counting number. But I really like thinking about it in terms of that equivalence of, I want a number of photons equal to that amount, and so I have to multiply by how much energy each photon is carrying. And that just makes more sense in my head. If the other way made more sense to you, great. So, going on, I've got one more question on the queue. So that was Mastery Question 1, Problem 4. And the last question I have in the queue for doing questions right now is Mastery Question Set 1, Problem 5. Okay. And then if there are more questions after that, we can go for them. In terms of, so Emmy, I saw your question, what makes a good scientific figure? There are videos on that uh, on the Canvas page, if you go to the week 1 page, the very bottom of it has a couple videos on what makes a good figure. It's a bit much to go over right now. Caitlin, did you have a question about this problem? I saw your hand raised.
Yes, I did.
Sure.
So it made more sense to me the other way
Great.
for calculating. But I just had a question about the 179.3. Where is that from?
The 179.3, that was by converting the energy of the photon from joules per photon to kilojoules per mole of photons.
Okay. Okay.
Right, so it's that conversion of saying, so this way is thinking about the energy that each photon is carrying. And since each photon is carrying such a small amount of energy, sometimes it makes more sense to think about how much energy a huge number of photons, a whole mole of photons carries. And that's where the 179.3 came from.
Okay, thank you.
You bet. Okay, going on to mastery question 5. This is a question about isotopes. There's not a video that really talks about isotopes that much. The textbook does a really good job talking about isotopes and doing isotope calculations. So if you haven't been reading the textbook, please, you should be reading the textbook, coming to office hours, watching the videos. We've got lots of resources to you to make sure you've got different ways to look at this material. So let's go ahead and read the question. Chlorine has 2 naturally stable isotopes, chlorine 35 and chlorine 37. The natural abundance of each isotope varies in different regions of the universe. That's not totally true. In the banana slug region of space, the molar mass for a sample of chlorine is 35.77968 grams per mole. Using only these 3 values, determine the relative percent abundance of chlorine 35. So this brings in a little bit of fiction so that we can have some variability to it. We need to understand what isotopes are in order to do this problem, and we need to understand what elements are. So should have our handy dandy periodic table someplace nearby. And we're going to go ahead and we're just going to do the same type of problem analysis we always do. We're going to write down the information that's given. We're going to figure out what it's trying to ask, and then we're going to see if we can figure out what the missing information is in order to solve the problem. Okay, so let's see what's given. We got isotopes, we got mass, we got a 35Cl with a mass of 34.96,885. And we've got an isotope that is 37 chlorine with a mass of 36.9659. And then we also have the molar mass of 35.77968. That's all given. We have to understand a couple things. One, when we're looking at these different isotopes, essentially what we're looking at is so the number in the top left corner, when we're looking at an element, we've got a nucleus with some electron cloud around it. Electrons. That's the nucleus. The nucleus has protons and it has neutrons. Right, and so that number in the top left corner is the protons plus neutrons. It's counting everything that's in the nucleus. The symbol there, the chlorine, the symbol is what gives rise to, is determined by the number of protons. So again, looking at the periodic table, every element on the periodic table has a different number of protons. The number of protons changes how many electrons are attracted, and it's not a circle usually, we'll talk more about that next week, but it affects how many electrons are attracted to the nucleus, and that number of electrons attracted to the nucleus is going to change the reactivity, the physical behavior of the elements. The thing that's interesting is changing the number of neutrons doesn't affect that reactivity. It just affects how heavy it is. So we end up with elements, things that have the same reactivity, that have different masses associated with them. And on the periodic table, all of those reported masses on the periodic table are weighted averages. So it's not just how much, it is not evenly split. It's not like it's half chlorine-35 and half chlorine-37. There's some natural abundance to how much each of these happens. The why for that, we've got kind of two different ways we can think about it. We can just say, oh yeah, that happens, and understand that. The why gets into nuclear physics. A little bit beyond the scope of this class, but there's some difference in how much each of these occurs in nature, and there's a reason why there's not a chlorine-36 that we see in the natural world. All of that's kind of beyond the scope of this class. It gets into nuclear physics. Really fascinating stuff, but not what we want to talk about right now. So we need to take into account that we've got an abundance. Right, and this is also what the question is actually asking us to find. It's not going to be a perfect 50-50 mixture, so I'm just going to say we've got some abundance X and we've got some abundance Y. And you'll notice the problem, again, we always want to make sure we know what the question is asking for. Is asking for a percent abundance of chlorine-35. That's what it's asking for. Now, what is the information we have that's going to allow us, or what's the information that's missing? This is the information we have. What's the information that is missing? So, well, we need to understand something, right? So we need to think through this, and we need to understand that when we say molar mass, that has a particular definition to it. So I'll read that because my writing is a little bit sloppy. Molar mass, the numbers reported on the periodic table, that is going to be a weighted average of all natural isotopes. It's important that we're reading the textbook, at least reading the definitions in the back of the chapters that we're learning from. So we want to do a weighted average of all natural isotopes should be equal to that. Let's go ahead and set up what a weighted average would look like. That would be 35.77968 is equal to the abundance of the first isotope times 34.96885. I didn't give myself enough space, plus the abundance of the second isotope times that mass, 36.9659. Right? If this was a perfect 50-50 mixture, I would just say this one plus that one divided by 2. Oh, right. Oh, let me give myself more space because I forgot an important thing. I forgot to divide by 2. So this is going to be 35.77968 is equal to X times 34.96885 plus Y times 36.9659 divided by X plus Y. Oh, forgot about that part. That would have messed up everything. So this is what a weighted average of all natural isotopes. If we had something that had 3 natural isotopes, we would have a third thing added on. We'd have X plus Y plus Z, and we'd have another isotope. We could do this for 4 isotopes, 6 isotopes, 20 isotopes, however many isotopes we have. The nice thing is, since this only has 2 isotopes, we can recognize that these stable isotopes must account for all of the naturally occurring material. So I can have X plus Y equals 1. That is to say, the abundance of the first one plus the abundance of the second one is going to be all of the stuff that exists. So it's going to be 100% of the material, or put into a decimal fashion, 1.00, 100%. The reason that's important, and this is kind of like the star of solving this problem. Right? Without this, we actually can't solve the problem. Without that logical step, the problem's impossible. Right? Because we've got an equation here with X and Y, 2 unknowns. We need a second equation so we can plug in, do a little algebra, do a substitute and solve. So we'll rearrange this. So we've got, since we're solving for X, I'll do Y equals 1 minus X. And then I can do 2 substitutions. One, I can recognize that X plus Y equals 1, so I've got a 1 there. And then I can recognize that Y is 1 minus X, so I've got a 1 minus X in parentheses there.
Explain where come from again?
Say that again?
Can you explain where the X plus Y equals 1 come from again?
Okay, so this was a logical step. This comes from the idea of all natural isotopes, right? Whenever we're looking at all natural isotopes, we know that the abundances have to add up to all of the stuff that exists. So that means that in this case where there's only 2 of them, X plus Y is going to be 100% of all of the chlorine.
Oh, so that 1 represent like 100% of everything?
Yeah, in the decimal fashion rather than the percent fashion. Because when we're doing the algebra, we want it in the decimal fashion, not the percent fashion.
And what about that blue part again? Sorry, I was missing that part.
This blue part?
Yeah.
So this is an equation out of the textbook that is essentially the mathematical equivalent of this definition of molar mass, which is a weighted average of all natural isotopes. So this blue equation is the molar mass is a weighted average, so it's an average of those 2 isotopes with a weighting by their abundance. So that abundance tells us how much each one counts.
And then those abundance are given in the problem?
They're not given. That's what we're trying to solve for. In your typical...
Y, and then X and Y are the abundance.
Yes, X and Y are the abundances we're trying to solve for.
And you're multiplying by the AMU of each one?
We can do it in terms of the AMU that are given or the grams per mole that are given. If you're looking at your kind of more simple version of these problems, the textbook has a, if you have it, if you're like, wow, I need more practice with this, the textbook has some fantastic examples in the back of the chapter, and then there's also the supplemental workbook on the modules that is more practice. So in our simpler problems, you're usually calculating the molar mass and you're given the abundance and the isotope mass. A little bit more straightforward. This one is asking us to do this problem kind of backwards. So before we jump into our calculator, we're going to do a little bit of approximate thinking. This number is approximately 36. This number is approximately 34.968. That's approximately 35. 36.96, that's approximately 37. So even though I said it's not a perfect 50-50 mixture, it's actually almost, right? 35, 37, 36 is directly between 35 and 37. So I'm expecting something that's pretty close to a 50-50 mixture. It's not going to be exactly 50-50 mixture because this is a little bit less than 36. This is, they're all a little bit less. So it's not going to be perfectly 50-50, but it should be something around that range. Are you ready for some algebra?
Mm-hmm.
Okay, let's do the algebra. We've got an expectation of the kind of answer we're expecting. We can do that one on bottom. So we're going to go ahead. This is going to take a bit of space. 35.77968 is equal to 34.96885x minus 36, distributing the 36.9659 to the negative x and to the 1. I'm going to get minus 36.9695x plus 36.9659. And I feel like I wrote it down wrong. 36.9659. No, I'm okay. Oh, I know why it seems like I forgot a digit. There's a 0 there, but I'm not going to worry about that. First algebraic step. I'm going to combine those two things in terms of x together, and I'm going to subtract the 36.9659 from both sides. Calculator, help. Oh, 9659. I appreciate any of you that want to do this problem at the same time, kind of follow along. Make sure I don't make any typos in my calculator. It's always frustrating. So those two numbers subtracted gives me negative 1.186. Over here I've got 34.9688 minus 36.9695. And I've got negative 2.000x. Last thing I'll do is divide by negative 2 to get my x value. And I get x is equal to 0.5928. That's our answer. That is the decimal answer. The problem is asking us to do it in the percent answer, so you just multiply by 100 and you get 59%. Close to 50%, not exactly 50%, but, you know, approximate. Our approximation wasn't that far off. Hopefully that makes sense. There's a lot going on in this problem. There's our understanding of what an isotope is. There's our understanding of how molar mass relates to the isotope mass and abundance. And then there's recognizing the fact that all of the naturally occurring isotopes add up to 100% of that element's existence.
So, can you explain what the percent abundance mean? I don't really know what it means.
So this gets to this idea that chlorine-35 and chlorine-37 don't exist the same amounts in the world, in the universe. According to this calculation, chlorine-35 happens more often than chlorine-37. And that's kind of a weird thing, right? We're not really going to get into the explanation for why there's more chlorine-35 than chlorine-37. That gets into nuclear physics and the stability of the nucleus based on the quarks and the gluons that hold it together, outside the scope of this class. For us, what we're really dealing with is we measure this in the natural world. We see this happen where one mass happens more than the other. Can we make sense of that?
Can you quickly explain why the division is x plus y?
Oh, this. That is because if you're doing a weighted average, you're gonna divide by the total abundance. For us, the x plus y is going to be equal to 1. If we were doing something that had 3 isotopes, you'd have x plus y plus z on bottom, right? That's part of this definition of a weighted average.
But wouldn't that still be 1 if it was 3 isotopes?
Yeah, it would. Right, so it turns out that as long as we're always taking into account all of the naturally occurring isotopes, it's always going to add up to 1.
Okay.
Now, I still like to include it because it gets to this definition of what a weighted average is, right? Average is you add the two things together and then divide by the number of things there are. So this is dividing by the weight of each thing added together. So I like putting it there for the definitional kind of idea, but it ends up always being equal to 1. Well, you're going to have different numbers than me. You still have to do your own calculation.
What's the point of them giving us the G over mole?
So that's the number you need here. You're going to have different numbers here for your different problems. So that number's going to be different for you. Yeah, so I'm doing the problem for the numbers I was given. I don't know if you were given the same numbers as me.
I see what you're saying.
I'm going to see if it works for me.
So what would that Y value represent?
So the Y value would represent the abundance of the other isotope. So the question wasn't asking about the abundance of the other isotope, but we know that 59.28% makes up the portion of chlorine 35, and then we do 1 minus that, so we'd have 41% would be the X value.
The Y value.
Sorry, the Y value, thank you, yes. So yeah, I got mine right. You're just going to have different numbers than me. So you're going to have to go through. The process is going to be exactly the same, but I'm going to caution you, make sure you understand why you're doing the mathematical steps. If any of the steps that I went over, you're like, no, that didn't make sense, you should go back, check the definitions, read the textbook in terms of the isotopes and that section in the textbook. So, but yeah, the numbers are going to be different for different people, but for my problem, I got it right. Let me see. So that was the last question I had on Q. I'm going to go ahead and... So the next question someone asked is, how do we find the concentration of a standard solution? This is looking at the absorption lab prep 2, part 1. And this is about dilution. So we need to know a couple things in order to do this. One, we need to understand the idea of molarity, concentration, right? And molarity is just one particular unit of concentration. There's a lot of different units of concentration, but for us in this class, we'll be using molarity. It has the symbol capital M, and all concentrations are stuff in a unit of volume or a unit of mass, just how much stuff is there in a big thing of stuff. And for molarity, the reason we like this in chemistry class is because it really gets down to the molecular understanding. So this is going to be moles of stuff in a total volume of solution. So we've got some big thing. Usually all of the things we're going to be looking at this quarter are going to be water solutions. So we've got something that's got a bunch of water and it's got like a little dye or a little sugar or a little salt, a little something in there. And we want to figure out how that changes if we add more water. If we change this total volume, the concentration changes. The way that we typically use this, the way we set it up, is we have molarity times volume equals moles of stuff. So that's going to give us a way that we're able to figure out how much stuff we have. If we've got the molarity of our solution and we've got the volume of our solution, we can get the moles of stuff. Now, if we add water to that, we're going to change the volume, but we're not going to change the moles of stuff. So if number of moles does not change, we can imagine if that's going to be the same, then we can have two different molarities, two different volumes. We've got M1 V1 equals M2 V2. So essentially, there's some number of moles equal to the same number of moles, even though our volumes have changed and our molarities have changed. So when we are given a stock solution, for me, I had a stock solution that was 14.2 micromolarity, and I had 15 milliliters. And I had 15 milliliters as a stock solution, and it diluted to a 50 milliliters total. And you'll notice I've got my first molarity and my first volume, and I've got my second volume. So the only thing unknown is that second molarity. We can go ahead and set that up. And the way it ends up getting set up is M1 times V1 over V2 is equal to M2. And essentially, what's nice about this is it becomes a ratio of volumes, which kind of makes sense, right? Keeping in mind that this is a difference by adding water. If we change the number of moles, this doesn't work. This is only if we're adding water. So it's a ratio of volumes. Since our first volume is smaller than our second volume, we're going to see the concentration go down as we add water. Concentration goes down. I like to think of it in terms of like homemade Kool-Aid, right? You put the Kool-Aid powder into your thing of Kool-Aid, and you can make some Kool-Aid. If you dump in a bunch of extra water, you're not really making more Kool-Aid. You're just diluting your Kool-Aid so it has less flavor. But now we can go ahead and plug in the numbers I have and see what we get. I've got 14.2 times 15 over 50 is equal to 14.2 times 15 divided by 50 is equal to 4.26. Notice that because I had this in micromolarity, I get it in units of micromolarity. Technically, this should be, normally when we look at our volumes, it's going to be in volumes in liters. Forgot to mention that earlier. We usually have this in liters for our standard definition. So technically, I should have done this as 15 times 1 milliliter, sorry, 1 liter per 1,000 milliliters, divided by 50 times 1 liter divided by 1,000 milliliters. But notice the 1,000 milliliters cancels out anyway. So we still have unit consistency because we have that ratio. If we were trying to find a number of moles, we'd have to convert to liters if we wanted to find a number of moles, just from the definition of molarity. So you find the volume of stock solution. That's given in the problem in part 1. So I'm going to go ahead and stop recording.